dive right into things. The most important thing for you to know right now, because the computation is going to come along as you go, the most important thing for you to know right now is the geometric interpretations of our cross product, of the cross product and the dot product. So let's do the cross product first since I'm stuck with it. So as a reminder, okay, and this is not a perfect illustration because why? Because the vectors v and w are just stuck in the yz plane for this demonstration only. Okay, for this demonstration only, these two vectors are stuck in this plane. But you could imagine them being anywhere, and everything I'm telling you is still true. So what is the cross product of the vectors v and w? Well, the cross product of two vectors, and they live where? Where are we in? We're in 3 space, right? And the cross product of two vectors is a new vector, also in 3 space. So all we need to know is its magnitude and its direction, right? How do we determine its direction? Its direction is determined by the right-hand rule in the order in which you do multiplication. So as I've set this up, we're doing the cross product of v and w. So we're going to take our index finger and point it in the direction of the first part of that product, the first factor of that product. So which one, v or w? V, index in the direction of v. Middle finger then in the direction of w. Your thumb is doing what? Pointing out of the screen. Okay? Now because my v and w are limited to the yz plane, my thumb will always only point out of the screen or into the screen because I can't move these two vectors out of the yz plane, right? But in reality, for any two vectors in 3 space, index finger in the direction of the first factor, middle finger in the direction of the second factor, however you're aligning them, and then your thumb is pointing in the direction that of the cross product. And remember that if I've got these two vectors, this is what in relation to these two? The cross product is orthogonal to both of them. Okay? This is so essential, folks. This is the knowledge you're building. Yes, computations are important, but this is the knowledge that you're building. Now, so for a new vector that we get by doing the cross product, we need to know its direction and its magnitude. So we've just discussed the direction. Okay? And just as a reminder, with this, I really like this demonstration. I do encourage you to play with it. If I were to swap this out, I'm still doing v cross w. So notice now my cross product is this vector pointing in the negative x-axis. Everyone check that. V cross w. V is your index. W is your middle. Your thumb's now pointing into the board. Everyone have direction down. What else do we need if we're going to give a vector? We just said it. We need the magnitude. How do we determine the magnitude of the cross product? Well, the length of the cross product vector is equal to the area of the parallelogram spanned by those two vectors. Folks, I found ways to test you on this knowledge separate from the computation. Okay? Christian and I met the other day. We went through a couple of good questions that go through how to test your knowledge of that without making you do any computations. Okay? They're hard questions. I highly recommend you speak with Christian during SI. Do we have SI today? Today, yeah. What time is it?
Right after class.
Right after class. So we've got SI today, and then I think you also do a virtual SI session on...
Not till Wednesday.
So not till the following Wednesday, but on Wednesdays we do virtual SI. Okay? How does that work, folks? Okay? All right. So that's our cross product. You need to develop that intuition, separate from our calculations. Okay? The calculations are important, but separate from that, you need to build that intuition. Then we had our dot product, and remember that the dot product roughly measures, here it's computing the dot product, the degree to which two vectors are pointing in the same direction. Again, I think this is a great little applet. Play around with it. Build your intuition as you work with this. This is all going to come back. One of the reasons why we're flying through this content right now is because all this content comes back in the final chapter of this course, which is the final part of calculus. Okay? The real understanding of calculus comes in the last chapter of this course. And we are racing to get there so I can give you as much time in that last chapter as I possibly can. Okay? And the nice thing about it is, these topics that we're doing right now, we come right back to them. Okay? So I'm trying to highlight the things that you have to master right now and the things that you get the whole semester to learn. Okay? All right. So that's our dot product. So we started these notes last time, picking up with them. From our pre-work, we said this is the way of describing a line. By the way, you guys have now done the next day's pre-work, and we could describe a line now looking at it as a vector-valued function. Now it looks like a vector-valued function where you input a t-value and it outputs a vector. And that traces out your line in whatever space you're in. The beauty of doing lines this way is you don't need to know what dimension are you in, right? These could be outputting vectors in 2 space, in 3 space, in higher dimensions. This equation stays the same. That's why we like vectors. So here we had this equation right here, this question right here, where we were asked to find the equation of a line passing through these 2 points. So, folks, the take-home from this, I'm trying to boil things down to take-homes. Okay, there's lots of challenging questions I can ask about any one topic. The take-home from lines is if I want to describe a line, I need both an initial vector that to give me a point that I pass through, that r0, and I need a direction vector. That's what we saw right here, right? This is just always any old vector you get out after you do this computation. T is a variable, a parameter that you get to pick. So the 2 things you need to know are an r0, which corresponds to some initial point that the line passes through, and a direction vector for that line. There's the picture. There's your initial that's your initial vector that gives you that first point, and your direction vector for that line. As I scale this black line, as t goes between minus infinity and infinity, I trace out that line in whatever space I'm in. So, what do you need to come up with the equation of a line? You need a position vector and a direction vector. You need both those things. So that's what we did here, right? We needed a position vector. We picked this one. We could have picked the other one. It doesn't matter. We just needed a position vector. Then we needed a direction vector. The easiest way to construct a direction vector was to say, well, let's look at the vector that points from P to Q. I could have also just easily done Q to P and switched that around, right? We're going to do the vector that points from P to Q. So we did the 5 minus 1, 5 minus 2, 5 minus 3, and we got our direction vector there. How are we doing? This now gives us the vector value equation for this line. We now actually, after last night's pre-work, have more skills, and we could have actually written this as a function, where you input time and it outputs what? Vectors. Folks, what's going in, what's going out? Your math teacher's been telling you about it all along, about functions, input, output. Now it matters, because here we input a number and it outputs a vector, right? In other problems, we will input points and output numbers. Okay? And math gets most generalized when you input a point this long and you output a point this long. Okay? And that's where you go after this class. All right. So this is our vector equation. Oh, Dan, sorry.
Just had a question with regard to which point we pick, because that changes the direction based on...
Ah, great question. But look at here. Let's say I had picked this. Great question. What if I say I picked this as my r0, and maybe I ended up finding this as my direction vector? It doesn't matter. As I scalar multiply that direction vector and add it to the original, whatever I'm using as a position vector, I'm tracing out the same line. Okay? So folks, that's going to be an important aspect of this class. We're going to touch on it today, called parameterization. We might pick different ways of parameterizing the line, but if we're tracing out the same line, we found an equation for the line.
Well, you had shown us in the video the way to reverse the direction.
Yes, but that's still the same line, right?
Yeah. So we'll just be able to tell based on the context.
So why is my job hard? You can do these problems many, many ways.
Okay.
Any way that's appropriate, I have to grade it. So I cannot have a key and say, nope, your answer is not the same as mine, you're wrong. I have to go through every line, every step you do, and as long as you are coming up with an equation of a line, you're good.
Okay.
You might pick a different parameterization than me, and both of our answers are equally good. Now, as we go further along, there might be a ideal way to parameterize a line that will make our further calculations easier. And that'll be something that we'll develop as we go.
Okay, thank you.
So the next thing is the parametric equations. So the parametric equations would just look like this. We would say that our x-coordinate would be equal to 1 plus 4t, our y-coordinate would be equal to 2 plus 3t, and our z-coordinate would be equal to 3 plus 2t, where I'm getting my x, y, z points, which are the tips of the vectors, from these row equations. Everyone see where I got these row equations from? Does anyone want to talk about that? So for example, we have 1 plus 4t, that's where I got the first one. 2 plus 3t, that's where I got y's coordinate. Okay? These give me the same collection of points that this version gave me. Folks, in this class, what's going to be challenging is, and we'll mention this today, I will swap back and forth as I need to, as it's convenient, between writing the vector equation of a line, the parametric equations of lines. We'll be jumping back and forth all the time. That's going to be challenging. When you're looking at somebody's key, my keys, somebody else's key for work, okay, you might have been writing it one way and I might be writing it another way. We might be both equally right, and that's going to be tough as we swap back and forth between all these different ways of representing things. One way that I will not do in this class, but I want to show you, because some Calc 3 teachers like to emphasize it, is the symmetric equations. So I will not ask you to do these in this class, but some Calc 3 teachers focus on it. What you do to come up with the symmetric equations is you solve each of the parametric equations for t. Solve each equation in B for t. Clean that up just a little bit here. So if I were to solve the first equation for t, I would have x minus 1 divided by 4. That would give me t, right? If I solve the second equation for t, that would give me y minus 2 divided by 3. So I'd have y minus 2 divided by 3. But what? They're both equal to t, so they are equal to one another. Okay. The third one is if I would take for z, to solve for t, I would subtract 3 and then divide by 2. So I'd have that that's equal to z minus 3 divided by 2. And then the t is what each one of these is equal to. These are called your symmetric equations. I'm going to show it to you. I'm not going to specifically ever represent answers in that way, but some teachers do. Okay? So, showing you that. Okay. So let's give several parameterizations. So careful here. What's the difference between question 3 and question 2, the first part of question 2? What were we tracing out in question 2? A line. What are we tracing out in question 3?
Line segment.
Line segment. So this has to have a start and a stop. In some ways, line segments then are harder than lines, because with lines, the domain of the parameterization will always be from minus infinity to infinity. Here, I better double check that I'm starting and stopping where I'm supposed to start and stop. Now, folks, now this part's going to be hard. And I don't know how to preface this. I've not yet found a calc book that says, let's just spend some time teaching parameterizations. Instead, they teach it as we go. Okay? So this part's going to be hard for this course. Okay? In a few days, you're going to say, wait, how do I know what parameterization to use? And the answer is, most of the time, it doesn't matter. That's the answer. Most of the time, it won't matter. As long as your parameterization traces out the correct graph with whatever stipulations you were given, you're good. Okay? What makes that hard is sometimes I might take advantage of symmetry and start throwing in sines and cosines because it'll make things easier, especially if my graph has some circular components. Other times I won't. Okay? That's going to be challenging as we go through this course. How do I know which parameterization to use? And the answer is most of the time it doesn't matter. As long as your parameterization traces out the curve, you're good. So a natural parameterization to use for this would be to take exactly what we just did right here. Notice that when t is 0, what vector does this equation spit out? The position vector that I started with, right? Point, in this case, that was point P. And when I get to t equals 1, plug in a 1 for t here, folks. We'd have 4 plus 1 times 4. That would give me 5. 2 plus 1 times 3, right? So when t gets to 1, where are we at? Q. I call that a standard parameterization. That's kind of my own word for that. Just a standard parameterization. It's like the most natural thing to choose in parameterizing this. Okay? So what we could do for a standard parameterization is say that R, that's fine, yeah. To say that R is equal to just the same, was that 1, 2, 3, folks?
Yeah.
1, 2, 3 plus t times what?
432.
432. Now, this is where you get into trouble. If you stop here, what are you giving me the equation of?
The entire line.
The entire line. And the whole point of these line segments is that you start and stop at the two endpoints. So notice that this holds for 0 less than or equal to t less than or equal to 1. Okay. How are we doing? Now, if I ask you to come up with a line segment, have we done it? Does our function trace out this line segment? So they said no. Do we doubt it? No? We're okay? Okay? This traces out this line segment. Okay. Yes?
Is there an easy way to find the domain of any?
So notice, because of the way I just found the equation of the line, how did I do this? I just picked one of the 2 points that I was given. I didn't go find a new point. I just took one of the 2 points I was given, and then I just found the direction vector by going from P from that start point to the next point. That gave me that direction vector. If you do this, then you will always just let t go from 0 to 1 if you set it up this way. Now, yeah, so does that make sense? So again, the first thing you should do, folks, is come up with the parameterization, and then the next thing you should do is test it, double check it. At least, now you're not necessarily right just because you get the start and end point right. Like what if this was like a spiral that eventually arrives at the other point? We didn't pass through all the correct points, right? But at a bare minimum, you ought to check that what you're claiming is the parameterization starts at one of the endpoints and stops at the other if you have endpoints. Okay. Great. Folks, this part is going to be hard. I am not looking for mastery on this today. Okay? You need to get this mastered by the time we get to chapter 17. We've got some time. Okay? But for right now, I want to convince you that there are many other parameterizations you could do. So for example, we could go ahead and reverse the direction of this parameterization. How would we do that?
Use Q as the initial point instead of...
That'll work. Let's do that. Okay. What I was going to do, I'll show you another way where you can manipulate the time value in here. Then that would give you, you would just flip-flop the time values. But then that doesn't make sense, so you'd multiply by -1 to make it make sense. And then you could go ahead and replace t with minus t. But that'll work too. So let's go ahead and do that. Let's go ahead and pick point Q, which was what?
5, 5,
5, 5, 5. And then we're going to have to come up with the direction vector QP, right? Well, notice that's just going to do what? It's just going to point in the opposite direction that our first one did, right? So that would be plus t times -4 minus 3 minus 2 for 0 less than or equal to t less than or equal to 1. Now, folks, something to keep in mind here is, let's just leave it at that. Yeah, good. Okay? So folks, we've come up with the parameterization. This does look like it's tracing a line. And what are we, sorry, if I didn't have the t value here, this is the equation of a line, right? Absent the t value. So that seems like we're getting to a line segment. And then what should we ought to check? That what I'm claiming are the two endpoints match the two endpoints. When t is 0, where am I at? I'm at Q. When t is 1, where am I at? I'm back to P, right? Does everyone see that? So we have indeed traced out the line segment that we're supposed to trace. So folks, if all I ask you for is a line segment, either of those two answers work, right? But if I tell you that your line segment has to start at P and end at Q, then you must give me the first one. Now you could give, there's other ways you could give parameterizations, but notice when I put in my lowest time value, I do indeed start at the right point. So that is starting and ending. There is a sense of start and end. We're going to talk about that later today. That's called our orientation to these curves. Okay, so let's go ahead and just speed up the parameterization here. Second. So how could we think about speeding up the parameterization? What we could do is maybe, let's go back to our original one here, and let's maybe go in half the time. So I'm going to use a different letter here so we don't get confused. I'm going to use the letter S, and we're going to do this parameterization in half the time. Now, we're going to have to make an adjustment here. Okay? So if I were to go ahead and, let's see, let me make sure I'm getting this right. Oops, give me a second here. Double that too. Yeah. That works. How do I want to say that? That's what we want. So let me show you how I came up with that, and then we'll make a substitution here. Okay? So I'm going to go ahead and let S equal 2t. That's going to have the effect of speeding up this parameterization. Okay? Again, you might be saying, Charles, how did you know to do this? Well, one, you see I didn't know to do it to begin with. But two, you just get practice with it as you go. So this is where I'm saying this is a skill that you're going to develop over the course of this semester. Okay? So if I'm going to do that, let's go back to this statement right here, that we have 0 is less than or equal to t, which is less than or equal to 1, and replace it, let's go ahead and replace, if we solve this for, let's see, 1/2 t, 2t.
Shouldn't it be?
I want this to be 1/2 t, excuse me. And again, folks, actually what I'm demonstrating here is how these parameterizations work. You pick something and then you adjust it as you need to. Okay? So I'm going to let s equal 1/2 t. So if I were to do that, this would imply that t is equal to 2s, right? So now what I'll do is I'll replace the t inside this interval with 2s. Okay? And if I solve this for s, we get 0 is less than or equal to s, which is less than or equal to 1/2. That's where I got that interval from. Okay? So what we'll do then is we'll take our same very original parameterization here, r is equal to, it's going to start at 1, 2, 3, but it's going to trace out this amount. Okay? What do we say we're going to replace t with? 2s. Then, this scalar multiple, I'm going to go ahead and distribute it into the vector. I'm going to bring it into the vector. I'm going to scalar multiply it. Okay. And if I do so, running out of room here. We get that r is equal to 1, 2, 3 plus s times 8, 6, 4. What did I just do here, folks? One way to interpret this is I just doubled, I scalar multiplied my direction vector by a factor of 2. Okay. We'll talk more about how that's related to calculus. What's the derivative of a line, folks? Just the slope. The derivative of a linear vector function will be just its direction vector. And I just doubled the direction vector, meaning I just doubled its velocity vector. We'll see more about that as we go along. We're not looking for mastery today. Okay. So everyone see this? But what? What do I always have to give? And I've already done so. What do you always have to give with any parameterization? The domain, right? Because no longer do I want 0 to, or t to, our time value s to go from 0 to 1, because what? I would overshoot where I'm supposed to stop this parameterization. Okay. I'm going to skip these two for right now. Okay. Again, we've got all semester to learn how to do this. This is our first introduction to it. If you're feeling a little confused right now, that's okay. I'm going to try to continue to highlight this as we go through this course. Okay. Let's go ahead and accelerate this. Let's go ahead and accelerate as we trace this parameterization. So what could we do here? We could, for example, take R is equal to 1, 2, 3 plus t squared times 4. What was it? Is it 432? Times 432. Notice that my parametric variable is no longer linear, so it's not going to trace this through at a constant rate. We're getting ready to talk about calculus, folks. This is going to trace this through at a rate of 2t. It's going to accelerate as we move through. It's no longer going to constantly trace it out. It's going to speed up as it traces it out. So I replaced my parametric variable with something that was nonlinear. Now careful, folks. Am I now describing a quadratic? I've got t squared there. Am I now describing a quadratic?
Still a line.
It's still a line. It's just that the rate at which I'm scalar multiplying my direction vector is what's speeding up. Increasing in velocity as I trace that through. Okay. So then what do we need to ensure? This is still tracing out a line, but we need to be a line segment, so we need to ensure that we're still tracing out. Let's see here. Well, if we do that, and then we go ahead and, that's not a domain, right? I got to tell you what t values to take on. So then we could go ahead and say, I kind of don't want to get into all the argument of it. Maybe you can just buy it 0 less than or equal to t less than or equal to 1. It'll still be from 0 to 1. It'll still arrive us where we want to get to.
Is that through taking the square root?
Yes, well,
the positive?
I don't know that you can go ahead and just say that you can take the square root of all three sides of an inequality like that. So I've not thought through that. But maybe you could just see that. Yeah,
Okay.
we'll talk more about that. Yeah.
If you square root it, shouldn't it be plus or?
So I didn't take the square root. So I didn't take the square root. I didn't apply a square root. You could.
What did you do?
Well, I'd rather do it by inspection if you don't mind, right? So to make my largest t squared value be 1, the largest input I should put for t is what?
1.
1, right? So one way you could say it is for the endpoint, if I want t squared to equal 1, then the largest value I want for t would be a positive 1. I wouldn't want to go from minus 1 to 1. Okay? What if you had picked, for example, this is actually a really interesting question, so I'll go off. What if we gone from minus 1 less than or equal to t less than or equal to 1? What would this trace out, folks? Still traces out the line segment, but what does it actually do?
Doubles its length.
It's true. Why? Yeah, Alex.
Wouldn't it just be 2, like, on top of each other?
So when t is negative 1, let's see here, what would we do here? We would go from when t is negative 1, from 0, we would go out till we got to 0. So when t is negative 1, we'd actually start at, here's p, here's q. So in this, using these values, we would start here and go out. Using these values, negative 1 to 1, we would actually start here and then go out. We would trace it, we'd start at q, tracing backwards, and then return. Okay? Typically when you give a parameterization, you don't retrace your steps. And so that wouldn't be a good use of a parameterization. It can cause sorts of confusion into other problems we do down the road. Okay? I don't know how much more I want to do, folks, because we're not looking for mastery today. All I'm trying to convince you is that there are many different ways that I could trace out this line segment. But I'll take them if you've got them. Hayden.
I just,
Christian, sorry.
I just kind of going back, is a position vector, is it always going to have a tail at the origin?
So whenever I write coordinates of a vector, I'm talking about a position vector,
Okay.
right?
Yeah.
So vectors, a vector as just an arrow containing magnitude and direction could be this vector right here. But as soon as I talk about the vector 1, 2, 3, it's implied that my tail is at the origin and my tip is at the point 1, 2, 3. It's that vector there. So as soon as I'm writing them in coordinates, I'm talking about position vectors. Now when we talk about this line is just the collection of all the tips of all these position vectors. So notice that we're adding vector v to it, but really we could move that vector v down here and then do our parallelogram law, and that would give us the other vector. So it all works whether we're doing it with arrows in space or whether we're doing it with coordinates. Yeah. Yes?
So when you said we never want to double back,
Well, typically if I say I want you to give me a parameterization for this curve, we don't want to double trace it. It might be, for example, like we're going to go along this curve and at each point we're going to evaluate something like the temperature along the curve and then get a sense of like an average temperature. We don't want to then double back through it. That can cause trouble.
so does that imply that for our domains and that, or those types of questions, we don't want there to be a sign change?
See, I need to be really careful here. This is where it's hard. This is why in one of my notes here I say no book gives you rules for how to do parameterizations. If I were to trace out this three-dimensional butterfly curve, I do have to trace it out, I will probably end up going through a point twice. So I don't want to say you can't go through points twice.
Okay.
It's very hard to give general rules for parameterizations. So let's just, again, I'm just trying to introduce it. I know you're going to struggle with it. That's how this course goes for a while, and I'll just keep clarifying it as we go. Okay. So I find that if I don't talk about parameterizations now, then when it's time to talk about them, it's too much. So we'll just keep going on. Let's do another one. Let's just do another one. I'm not going to go into how I get the domain for it. Let's just do it. We'll do 1, 2, 3, and then I'm going to put plus e to the t 4, 3, 2, and then what? I need to make sure. Oh, is that going to work? That's not going to work. Never mind. That's not going to work. I guess we could just do. Let's just do for a second 1, 4, 3, 2. We'll just do t to the 4th power. Something like that, and that'll still go from 0, less than or equal to t, less than or equal to 1. Okay? The point being, folks, is not how did Charles come up with each one of these. The point is that each one of these parameterizations does what? Traces out the exact same line segment. Okay? So one of the things that as we're doing this, we're going to be developing calculus, and it's going to be important that we don't restrict ourselves to just a certain parameterization. The ideas we build need to work regardless of what parameterization you use. Okay, that's going to be an interesting point as we go along. Okay, here we go. So there's that statement. Students often struggle with coming up with parameterizations. We will get much more practice over the course of the semester, but as a rule of thumb, you ask the question, does my parameterization trace out the curve? If so, great. At this point, you're doing what you need to do. Okay? All right. Let's summarize. To build an equation of a line in 3, so folks, this is the take home, okay? So folks, I see this every semester. We get, I don't always teach this class, but I often tutor for it, okay? And I'll see every semester when people go back to review lines and planes, they've forgotten everything they've learned, okay? And I'll say, well, what do you need to build the line? And they'll say, well, this is asking me about lines being perpendicular, and I've got vectors pointing this way, and all this. And I say, no, what do you need to build a line? You need a position vector and a direction. I will ask you, and this is where I will not cover in class or ever all possible questions I can ask you. I will give you problems where I'm asking you to come up with the equation of a line, so what do you need to do? You need to find a position vector, and you need to find a direction. within the context of whatever question I've given you. We'll see that happen later on in this handout. Okay? So to summarize, to build the equation of a line in 3 space, we can use many different forms, but all require us to know a point and a direction vector. And folks, as we've mentioned, I'm moving back and forth between the point x naught, y naught, z naught, and the vector x naught, y naught, z naught. Whenever we need to, we make a comparison between the two. All right. Let's get into this. This is, I think, the one example where I wouldn't expect you to be able to construct the answer to this on first try. Okay? So I've got to show you how to do this problem. I think that everything else in here, once I get through this, as far as lines go, once I get through this example, everything else here is just extensions of what I've already covered, which is, what do we need to build a line? A point and a direction vector. All right, here's a really challenging application, I think. And it's challenging because there's lots of ways you could go about doing it, and we're going to find the most, kind of the shortest way, the most elegant way of coming up with a formula here. Okay? Consider a point and a line described by this equation here. Find the minimum distance between the point and the line. Okay? Folks, one of the skills that you want to develop in this class is sketching a picture to this problem. Now, I didn't tell you what this line was. I didn't tell you where in space this point was. You don't have to draw an accurate picture. You need to draw sort of a cartoon representation of the problem. Okay? You don't have to draw an accurate picture. It just needs to be a picture that gets the essence of the problem down to give you a little bit of guidance. So I have some students say, Charles, I can't draw, they'll say, I'm having a hard time drawing this line in 3 space. Great, so am I, right? Okay. And I'll say, you don't have to worry about drawing a super accurate picture, right? Then I'll have other students, and they'll say, Charles, I don't know how to do this problem at all. And I'll say, where's your picture? You need to draw a picture, not a perfect picture. Okay? So let's draw a picture for this, folks. We've got a point. Where's our point? I don't know, maybe right there. Everyone see it? There's our point. And we've got a what? Line. We've got a line. There's our line. Everyone see it? Now, what do we need to do? Our goal is to find what?
The distance between.
What distance?
The minimum.
The minimum distance. I don't want to find the distance between the point and this point on the line, or the distance between the point and this point on the line. I want to find the minimum distance. Okay? Let's label that point P. So what's our goal, folks? Our goal is to find this minimum distance right here. Our goal is to find that. How are we doing? Okay. There are many ways you could go about doing this. I've had some students want to start doing calculus, and that's a really good intuition, right? Why? Because you've learned whenever you see the word minimum that you're thinking about minimize. Okay? There's an easier way to do this problem. So you could come up with a distance formula and then try to minimize it. We will learn how to do that when we get to the method of Lagrange multipliers. Okay? We'll learn how to do that then. But for right now, there's actually a very elegant formula that we can come up with for this. Okay? The trick is, I know that I've got some point, let me do it in a different color. I've got some point on my line corresponding to the vector r naught, right? So folks, notice I wrote this as a what? A point or a vector?
Point.
I wrote it as a point because I didn't put an arrow over the top and I didn't draw the arrow. But it corresponds to the vector r naught, right? Okay. And then what else does this line have? Folks, again, we're trying to boil this down to as simple as possible. What does this line have? It's got an initial point and a direction vector. Let's put the direction vector on here. What direction is this line heading in? How about this direction right here? There's our direction vector v. Okay. We're setting ourselves up, no matter where this line is in space, no matter where this point is in space, and in fact, folks, what? Whether we're in 3 space or 2 space or 4 space, nothing about what I've done has relied on being in R3 right now. Okay? Regardless of what dimension I'm in, I can construct a right triangle here, right? So again, folks, don't worry about your picture being accurate. You got a point, and you've got a line coming through. You can then construct a right triangle from it. Okay? So if only we knew this angle theta right here, we could start doing some trigonometry, right? What are we trying to find here? What's our goal? To find the what side of this triangle? To find the opposite side of this triangle right here, right? So if I knew this length and I knew this angle, we'd be good. So in fact, we would say, so what's this length right here, folks? The length of this green line right here, what's its length? It's just the magnitude of this vector connecting R naught, which I have, and P, which I know. Okay? So let's take the magnitude of that vector and multiply it by the sine of the angle, and that will give us our distance D that we're after. Having fun yet? I'm just getting started. Okay? How do you feel about that answer? It's an answer, right? Right? If only I knew the angle between these two vectors, right here, then I could just compute this, right? Why don't you like this answer?
We don't know.
We don't necessarily have that angle. Or can we find angles between vectors?
Dot product?
We have tools. Dot product's one. Yeah. In fact, that was my first guess when I was trying to remember how to do this problem. My first guess was to go to the dot product, right? Because what is the dot product of two vectors?
A measure of to what degree they point in the same direction.
Very good. And we have a geometric way of finding that. And it's the magnitude of the first times the magnitude of the second times the what? Cosine of the angle between them. So if I knew the length of this vector and I knew the length of this vector, I could find the angle between them, right? Do I know that? Yes. But notice that this, and this is how I was going to do it beforehand, notice that this involves me actually using my inverse cosine function to figure out what theta is. And it just makes it a little bit messier than I want. And what? Once I find theta, what do I want to do with it? I want to take its sine, right? So folks, this is a clever skill. Yes, we had a formula already that I gave you that enables you to find theta somehow. But why do I want to find theta? Because I need to know what sine of theta is. Did I give you another formula that enables us to immediately find sine of theta? Do you remember what that one is? It's okay if it's rusty, that's all right. When we were doing our cross product, we talked about the cross product finds the area of the parallelogram. How do we find the area of a parallelogram? It's going to be the base times the height. How do we find the height? Well, if we know this angle theta here, this would just be a sine theta, right? Okay, remember that? So that gives me the area of a parallelogram. Why are parallelograms special? Areas of parallelograms, why is that special for stuff we know?
Because you can take the magnitude of the cross product.
The magnitude of the cross product will give me that area which has a sine value in it. Okay? So I gave you a formula last time, so this would be okay, but better was this formula from last time, that the magnitude of u cross v was equal to the magnitude of u, magnitude of v, times the sine of the angle between them, and that gives me the sine that I want. So I'm going to take this equation right here, tailor it for my vectors that I have, v, and this one's got a crummy name, r naught p, that's a crummy name for a vector, right? It's what vector? The vector connecting r naught and p. Okay? So I'm going to, my u will be r naught p, my v will be v, and then I'm just going to solve for sine of theta. So in general, the sine of the angle theta would be magnitude u cross magnitude v divided by magnitude u magnitude V. And for r's, we're not using u. What are we using? We're using this crummy named vector r naught p. Who's lost? Great. Let's talk about it. Okay. So this vector right here is this side of the triangle, the hypotenuse, right? So we clear why if I take the hypotenuse times the sine of theta, that'll just give me the opposite side. You okay with that? Everyone okay with that? Okay. So this could work as an answer. Yes, Alex.
Could you go over that again? Like
Sure.
It's like
So
sine
for any triangle, we label this side hypotenuse, this side opposite, this side adjacent. Okay. The sine ratio, the sine of the angle theta is the ratio of the opposite over the hypotenuse. I know you know that. But notice then if I solve this for the opposite side, I would multiply the hypotenuse over. Right? So that this is an equally valid formula. The hypotenuse times the sine of theta is equal to the opposite. In the context of my problem, I want to know the opposite side, so I'm going to take the hypotenuse times the sine of the angle theta to give me the length of the opposite side. Okay? How's everyone doing? Okay? So this is what I'm after. The problem is that this has a sine formula in it. So I took some other formula that we've already built that has a sine in it, and I've solved it for sine of theta. Good. Things are clicking. Good. Okay. Do you see that?
I don't understand why having sine in it is a problem.
Well, because in this problem right here, I didn't tell you what the angle between R naught and P, I didn't tell you what that angle was, right?
Okay,
So you don't have it.
okay.
So even though this is an answer, it has a variable in it that we could, through some hard work, go off and find. But let's be more elegant. We had a formula that has a sine of theta in it, so let's try to use that one.
Okay, I see.
Good, thank you. These are great questions, folks. All right, so if I were to take this formula, all I'm going to do is I'm going to take this formula right here, but I'm going to tailor it for the fact that the u, which is the first vector that I'm crossing with the v, is actually r naught p. Does everyone see that? So I'm going to replace u with r naught p. Okay. So this would be equal to r naught p, that's the one that was already there, and then this is my substitution, where u is equal to r naught p. So I'm going to do that substitution, so here it is. This would be u, I just wrote u. R naught p cross v divided by r naught p, magnitude r naught p, magnitude v. What happens? The r naught p factors cancel, and we end up with actually a decently elegant formula that we can use, where if we want to find the angle, or sorry, if we want to find the minimum distance, between a point and a line, we can just take this computation right here. Okay. So again, that's the take home. So folks, I encourage you to practice this derivation. Knowing this derivation is not essential for the course. I encourage you to practice it. Okay. So the take home formula is that the distance is equal to r naught p cross v divided, and that's a magnitude, divided by magnitude v. That's the distance between some arbitrary point and some arbitrary line in whatever dimension we want. Which is pretty cool. Again, what's cool about what we're building here is oftentimes we're doing it without coordinates. We're not restricting ourselves to 3 dimensions, 4 dimensions, 20 dimensions. It's pretty cool. Yes?
Where did that extra R naught P come from? That's like outside the...
Okay, so in this equation right here, great question. In this equation right here, I replaced all of the u's with r naught p's. Okay, so that's what I've got in red right here. This was the original r naught p sine theta, so I copied down the r naught p, and I've replaced the sine theta with everything in red. So here's this equation that we built, and I'm going to replace the sine of theta with this formula. Okay? No.
I just can't see. I'll
I
look at
can't
it
see
later.
what you're doing. I'm sorry.
I'm sorry, folks. They gave us this tiny room. They gave us these brand new boards that jut out 5 feet into the stinking classroom. Sorry. Please shout out. Don't wait a while. Be like, move. Just say move,
I'm
and I will move.
sorry.
Any of you, please. If I'm in the board, I need to sometimes, because these, you've seen me try to write on it. I can't write the way I'm used to writing, so I have to stand in front of things, but then you got to remind me to move. Okay? So just anyone in here, anytime, just give a move. That's good enough.
One more quick question. Where did the R naught P vector in red, both of those, where did those two go when you simplified down to the full green?
So this factor right here canceled with this factor right here.
Okay.
So these two factors cancel. Yeah. Jordan.
How did you know to replace U with R naught V and not V? Or R naught?
Okay, so this is a formula that's true for any two vectors, right? For any two vectors, this formula is true. What are my two vectors in this problem? V and this green vector. What's the name of this green vector? I didn't give it a name, right? But what does it do? It starts where?
R naught V.
And it stops at P. So what do we call this vector?
R naught V.
R naught P. So this is the first vector that I'm crossing with the second vector. So I take my generic formula. So folks, this is just, these are arbitrary letters. These could be A's and B's, U's and V's, X's and Y's. Usually we don't do that because that's variables. But these are just, this is just an arbitrary formula with vectors whose names are U and V. Okay? It just so happens that we already had a vector on our board called what? V. I could have, if I wanted to, call this vector U, but it's not very natural to pick that name, especially since we're doing things in terms of points. Who had questions? Alex, we okay with that?
Yeah.
All right. So folks, practice this derivation. If you're finding this derivation challenging, spend 10 more minutes on it and then come see me in office hours. Folks, my sole interaction with this class at this point has been talking about, can I get extensions on assignments? That's fair. My favorite thing to talk about is math. Okay? I'm not very good, right, at organizing stuff. I am good at talking about math. Come on by during math hours, or during my office hours. I would love to talk math with you. So if you find this derivation challenging, spend 10 more minutes on it, then come by and see me and we'll talk about it. I'm telling you that it's not essential that you build this, but here's the formula. This formula does what? It tells you the distance, the minimum distance, between some arbitrary point in 3 space and some line whose equation was this. Okay? So let's practice it. Okay? So let's practice what we learned here. Here I've got a point in 3 space. Here I've got a line. Folks, should you draw a picture?
Yes.
Yes. Should you draw an accurate picture? No. There's the point P. It's not in the right spot. Here's my line L. It's not in the right spot. Okay. This line L has some R naught on it, and it has some direction vector V. Let me extend that. One thing I want to make sure is that you don't think that the direction vector V has to lie immediately. It doesn't have to be the same length as the minimum. So I'll just extend that a little further. Okay. My goal is to do what? Find the minimum distance D between this line and this point. Okay. So D, we just said, was magnitude of R naught P cross V divided by magnitude V. Folks, what's our R naught in this problem?
3, -4.
Here R naught is the vector
4, 3, -5.
4, 3, -5. So careful, Isabel, this was our arbitrary point that's in space. This is our line. R naught refers to the initial vector point or initial vector on that line. And then V is the direction vector, which is what I multiplied to T. So folks, you notice you can just, by position, the same way, folks, you all know this. If I say I've got the line y equals 3x plus 2, what's the slope of that line? 3. How do you know that? Because the slope is what you multiply to your variable. Okay? What's my direction vector? Minus 1, 2, 3. How come? Because that's what you multiply to your parametric variable. Same way we do that with slopes. Okay? So what's my direction vector here? I just said it. Negative 1, 2, 3. Okay? All right. I'd like to leave this problem at that because we're trying to make up some time here. Okay? Does everyone see that this is now a plug and chug problem? You're going to find the magnitude of v. Does anyone want to find the magnitude of v? Should we practice that? What's the magnitude of v? That's the size of the vector, right? But it's a position vector, so we know one point is 0, 0, 0, and the other point is its tip, and so we can just use our distance formula on it. So this will just be the square root of negative 1 squared plus 2 squared plus 3 squared. That's how we find the magnitude of any vector. Okay. So folks, at this point, this problem has become kind of a plug and chug. You're going to take R naught P. I guess let me give that to you too. What's R naught P? Well, it's got to be a vector whose tip is at P and whose tail is at R naught. So all we'll do is we'll just do 3 minus 4, negative 1 minus 3, and 4 minus 5. We took the tail minus the tip, and that will give us that vector.
Isn't that the vector P R naught, not R naught P?
We took P.
Or am I?
Nope, you got that backwards.
Okay,
Yep.
I see.
1 minus 4 minus 1.
Well, 5 is
Oh, did I make a mistake?
5 is a negative, so it should be 4 plus 5, right?
It should be 9.
Great catch there. That should be minus a minus. Thank you.
And then is the 1 negative as well?
Oh, boy. Help me out, folks. 3 minus 4 is negative 1. Minus 1 minus 3 is negative 4. 4 minus a minus 5 is 9. All right. How are we doing? All right. So at this point, you see that you know R naught P. You know V. So what can you now do? You can now take their cross product. And then you can take the magnitude of that cross product by using the same magnitude formula. Then you'll divide that by the magnitude of V, and you'll have the minimum distance. Okay. From our pre-work 2 nights ago, from our pre-work, a plane is a collection of all vectors with a tail at some point P naught. What word goes here?
Orthogonal.
Yes, orthogonal to some other vector called the plane's what?
Normal vector.
Normal vector. Okay. So folks, I sometimes have people, they'll say, hey, I'm having trouble on this, the planes, my math lab. And I'll say, okay, how do you need to find a plane? And they don't know this part. Okay. This is the essence of finding a plane. Okay. This is, oh, we have trouble here. Can we read something? Please, folks, I do ask, so feel free to, as we're doing this, take whatever seat works well. I'm happy to zoom in and zoom out as you need to. If it's my crummy writing, just say I can't read it. But
I can't read the word before vector.
Normal.
normal. Sorry about that. Thank you. This is the word normal. Thanks, Elise. I appreciate you letting me know. Normal. Okay. And this was the word orthogonal. All right. So, given a point P naught and some non-zero normal vector, the set of all points P, which then you can construct a vector So if they're orthogonal, is called a plane if we're in R3, but if we're just in Rn here, what do we call it? We called it a hyperplane. Okay. Do I do it on the next page? No, so let's do it here. The picture that goes with this, folks, is the same picture that I gave you in your pre-work, but it's worth doing a quick review. Okay. I'm going to take some common point right here. Feel free to shout out to move, folks. I don't know why they put us in this room with this. I don't know what to do. Okay, and they won't listen to us. We send in requests saying this isn't working, and they say nothing. Okay. So please just shout out move. Is everyone okay? So here's this point P, and what do I want? I want all the vectors whose tail is at P and is orthogonal to some normal vector V, or some normal vector, I guess N here is what I'm using. So I want all of the vectors that are orthogonal to it. So for example, this vector right here that I just drew is orthogonal to N. This vector right here that I just drew is orthogonal to N. This vector right here, and I want that entire collection of vectors, and what do all the tips of those vectors form? The points that are in this plane. Okay? That is a very tough way to define a plane. It doesn't fit at all, for those of you who've worked with planes in earlier classes, it doesn't fit at all with the way it was defined to you. But this is how we're defining it because it extends so nicely for everything we want to do. Yes?
So planes are not infinite in this context?
I drew this as it, so when we draw planes in 3 space, we usually put a boundary around it, not because there is one, but so you can see it.
Okay,
Right? Like, how do I draw a flat surface that goes on forever
fair enough.
in this space? So usually we put a boundary on it, knowing that, understanding that it just continues as is.
Okay.
Yeah. So that's a plane. So the thing to know, folks, is this part, like you need to know and think about and consider this definition. If you don't know it, I can't explain it much better than I did in the pre-work. I'll be happy to try. Come by and see me in office hours. I'll be happy to try. But my recommendation would be to rewatch the pre-work where I gave you that definition. Okay? It's the collection of all vectors whose tail is at P. And it's just not all vectors, right? Like I don't have this vector coming out of the board right here. It's not that one. Why not? Because that vector is not orthogonal to our normal vector. It's all the vectors with a common tail at one spot that are orthogonal to this blue vector here called the normal vector. Okay? It's going to take a little while, so we're going to quickly get to applications down the road that allow you to keep coming back to this idea so that you understand it better. Okay? So one thing that I find really interesting is seeing how this ties into our original definition of a plane. Okay? I actually really like writing planes the way I did in your pre-work. How did I write it in your pre-work? I said it's a collection of points P that look like X, Y, Z, so that what? When you take N dotted with P naught P, what do we need? If this is some vector to be in the plane, if I want to force this vector to be in the plane, what do I need it to be?
0.
What do you mean 0? Not the 0 vector. I need this vector right here to be orthogonal to this vector right here. So I need their dot product to equal 0. Okay? It's actually like that whole messy sentence that I just wrote. A plane is a collection of all vectors with a tail at some point P naught, orthogonal to some other vector called the plane's normal vector. It's pretty amazing to me that we summarize that whole sentence right here. It's all the points that satisfy this. This equation right here. All points satisfying this equation, satisfy it. Now folks, it's kind of hard to see that that's even an equation at all. So but what we're going to do is take this very compact, and this is going to be a refrain of this course. I'm going to give you compact notation that fits with our definition, and then I'm going to teach you how to expand it out to something that's workable. Okay? Usually, this is where you develop the understanding, and the expanded notation is how you do the computation. Okay? So let's get there. So we've got...
Can you explain
explain that to me one more time?
So what type of vector is this? This is a vector whose tail is at? So remember, when I just write a vector like AB, it's understood that I'm going for, this is this vector that's
tails
constructed.
Not, and
Aha. So that this vector right here is this arrow,
yes.
starting at A, stopping at B. Okay? So this vector right here has a tail at
P0.
P0 and some arbitrary tip. Why am I saying it's arbitrary? Because it's just the coordinates x, y, and z. I haven't specified what it is yet. How do you figure out what x, y, and z are? You ensure that x, y, and z make this equation true. So let's go ahead and explore it, because there's still a little room for confusion here, so let's keep diving down into it. Okay? First of all, we'll write n dotted with, how do we construct a tip-to-tail vector? We would do x minus x naught, y minus y naught, z minus z naught. What am I doing there? I'm taking the tip minus the tail to give me each of those components of the position vector. And we want this to come out to be what? 0. So what's our normal vector? It was the vector ABC. We want to dot it with this vector x minus x naught, y minus y naught, z minus z naught equals 0. Okay. Folks, if you're finding taking the notes is getting, maybe jot down what I say. Like one thing you might want to do is, these notes are available online, right? Okay. So you can pull them up afterwards. So that's maybe something you can do if you're finding that's getting a little bit unwieldy. Okay. All right. What does this mean? What's this operation here? No. It's the dot product, right? So we can't multiply two vectors together. That doesn't mean anything. We can't say what's vector A times vector B. We do have two types of vector multiplication that we've learned. One is a dot product, and one is a cross product. But the cross product's limited. It only works in what dimension? R3. Okay. So this is a what type of product here? Dot product. How do we do the dot product? We multiply like coordinates together and add them up. Exactly. So here this would be A times x minus x naught plus B times y minus y naught plus C times z minus z naught needs to equal 0. Okay. If I were to just collect these points, folks, I don't want to write this equation 3 more times. So here's A times a number, here's B times a number, here's C times a number, and I'm going to add those all together and I'll call it D. Okay? Folks, I can tell we're feeling a little overwhelmed. This is the variable X, this is the variable Y, this is the variable Z. Everything else is fixed, where this was a fixed point X naught, Y naught, Z naught. Maybe imagine it as 1, 2, 3 if you like. Okay? And this is a fixed normal vector. Maybe it's 4, 5, 6. It's fixed. Okay? The variables are X, Y, and Z. Okay? So I'm going to distribute the A through, distribute the B through, distribute the C through, and I'm going to collect everything that's a constant and call it D. So that would give me, to collect everything as constant, I'm going to take it over to the other, I'll leave it there, that's fine. So we get AX plus BY plus CZ plus D is equal to 0, and that's the equation, for those of you who've studied planes elsewhere, that's the equation of a plane that you've used. Okay? Do you see that we can get back to that algebraic equation from our vector definition? So folks, the take-home point on planes is what? If you want to come up with the equation of a plane, we need what? A point, P.
And a direction.
Nope. That's for a line. So for a line, we need a point and a direction vector, a point that it passes through, and a direction vector. What do we need for a plane? We need a point and a normal vector. What does the word normal mean in this context? It means orthogonal. It's a vector that's orthogonal to all of the other vectors in the plane. Okay, so folks, here's the example of how you find the equation of a plane. Now, I want to point out, in this problem, right, let's see, where's the next one? I ask you to find a plane, line, parametric, find the minimum distance, find an equation of normal line. Oh, no. Find an equation to a plane. In this case, I gave you the point in the normal vector. That's actually an easier problem. Find an equation of a plane passing through this point and containing this line. That doesn't look anything like the problem I just showed you. It doesn't matter. What are you trying to come up with? The equation of a plane. So what do you need? You need a point and a normal vector. That's always what you need. So somehow in this problem here, I'm going to give you enough information to do that.
Quick question about normal vectors.
Yes.
Can they point either direction?
Correct. So I'm hopefully using the phrase a normal vector.
Okay.
Okay. And a normal vector is just any scalar multiple of a normal vector is also a normal vector.
Okay.
Yep. So again, somebody might pick a different normal vector than I did. As long as our two vectors are parallel to one another, we must both be right.
All right.
Yeah.
Thank you.
So folks, here's this problem here. We're trying to come up with the equation of a plane. What do we need to come up with the equation of a plane? We need a point. Do we have that? Yeah, we got that. We got plenty of that. We got 3 of them. What else do we need? A normal vector. I didn't give you a normal vector. This is where, what's that? This is where you draw a picture. Do you draw an accurate picture? No. You draw a picture. What did I give you? 3 points. From those 3 points, you can construct a plane, right? Now, what are we hoping to find? So, folks, I may have lost you in some of the earlier work we did with planes, but this is where we bring it all back. Okay. What do we need? A normal vector. That normal vector ought to be what? Orthogonal to all the vectors in the plane. Do you see any vectors in the plane?
Yes.
I don't see vectors yet. What do I got? Just points. But what can I do? I can create 2 vectors. Then, because vectors just have what? Direction and magnitude, I can put that normal vector right like that. So how am I going to find how am I going to find this red vector here? I need everyone to know that. How am I going to find this red vector right here? I'm going to take the cross product of any 2 vectors in the plane, and I'll be able to find the normal vector. Okay? So let's give these some names. Let's call this U, and let's call this V. So taking any one of my points and calling it the common point. Okay? So let's give these points names. Let's call it P1, P2, and P3. Okay? So let's find the vector P1, P2, and the vector P1, P3. Does that make sense, folks? I mean, so somebody else might take different points. They might come up with 2 different vectors in the plane than I did. But when we go to compute our cross product, we'll still have a normal vector. We might not have the same normal vector, but as Dan said, one would be a scalar multiple of the other. Okay? So I can construct 2 vectors from this. The first vector would be the vector, let's see here, we would do 2 minus 1, 0 minus 1, negative 2 minus 1. That's the first vector. That's what I'm calling vector, I guess, U here. I'm going to put that in green, folks. So we did 2 minus 1, 0 minus 1, and negative. Sorry, folks. Back to the drawing board. Let's see here. Give me a second, folks. I'm recopying what I had, I think. Okay. Everyone see how I'm finding this vector right here? Okay. Now, what is something that you have to make sure you get right about this? Okay. To be a plane, it's a collection of all. So you need it's a collection of all vectors whose share a common tail. So it is important that I have P1, P2, and then this would have to be P1, P3. I could have done P2, P1, but then this would have to be P2, P3. So you have to have the common tail there. Okay. So our vector U would be the vector 1, -1, -3. How we doing? And our vector V would be the vector 1 - 1, 0 - 1, 3 - 1. How are we doing? Okay. So then that gives us the vector 0, -1, 2. What have I got now, folks?
Got your first vector.
That's the first one. I've got two vectors in the plane, right? What am I trying to find? Right? What's the whole point of this, folks? We want a point. Do we have a point? Yeah, we got 3 of them. And we need a normal vector. That normal vector is orthogonal to all vectors in the plane, right? So we could just take the cross product of these two. So let's do that. Now, folks, should I take V cross U or U cross V?
It doesn't matter.
It doesn't matter in the sense that either one gives me a normal vector, right? Okay, so careful, because does order matter with cross products? Yes, but if you swap the order, you're still going to get a vector that's orthogonal to both of them. It'll just be, you would just be, instead of finding this red vector pointing in this direction, you'd find a red vector pointing in the opposite direction. That still works.
Does it change the sign or does it mess with it in any way? Or
So here's a fact. I don't know if I've spelled this out. I think you'll see it just doing some practices.
Would
But
it
this
one be like pointing the opposite way?
that's so that would be minus the vector v cross u. Exactly. So they're just opposite in sign. That's not a, it's a parenthesis. So interchanging the order of the cross product changes the answer, but it only changes it by the sign. So if we were to go compute u cross b, folks, remind me, it's been a while since we did this in class. How do I do this? Ooh, yeah, we can use the right-hand rule to decide the direction, but here we actually want to find the normal vector, right?
Yeah.
So I don't just want a picture of it, or I just don't want to think about it. Here I'm actually doing the computation. So how do we do that actual computation? We find the 3x3 determinant along with the kind of made-up vector ijk. Okay? Again, folks, this is just a gimmicky way to ensure that we find the what? The area of the parallelogram span between them. Okay? Find a vector that does that, I mean. So then, whose magnitude is that? So this would give us 1, -1, -3, 0, -1, 2, and we'll compute that cross product. The way I've shown you how to do it, and the reason why is because you go to other classes, this carries over to higher dimensions. This, not the cross product, but this calculation does. Okay, is to do this process called expansion by minors. Oops, that's a minus. So folks, what am I doing here?
You're multiplying and adding.
We're computing this cross product, but this process is called expansion by minors. Does everyone see it? Okay. Folks, you're gonna have to bear with me. I have to write big with this thing, and I'm not gonna do the best. My recommendation is just always kind of write a little small as you're working through these, and I apologize that I'm not getting the positioning on the board great, but it's just how it goes. All right, when I do this cross product, we got -1 times 2, -2, minus a positive 3, minus a positive 3, so it'd be -3, so I get -5 I hat, -2 j hat, -1 k hat. Just double check that. It's -2 minus positive 3. Yep. So I get as a normal vector, I get the vector -5, -2, -1. How do we do it? How are we doing, folks? Did we get that? Okay. All right. Now that I've got my normal vector, what can I do? I've got a point that we pass through, and I've got a normal vector. Let me give you a chance to get caught up with that.
Solve for D.
Solve for D. D was what we were using for the distance. D was the letter we used for the distance between some arbitrary point and some line.
But don't we have to use it as the constant in our equation as well?
So if you're going to go ahead and give the algebraic way of describing this, what you're welcome to do, you would expand everything out, collect all your constants together, and that would be the constant D. Yes. But in this case, we're not even to the point where there's a D on the board here, right?
Yeah.
So we need to come up with the equation of the plane, and because we're developing everything in terms of vectors, we're not talking about A, B, C in that sense, although you could say that's my A, that's my B, that's my C. But instead what we're going to do is we're going to go back to the original definition that we started with, the vector 1. So folks, we all caught up with this cross product? Okay. So then what are we doing? We're going to take n, and we're going to dot it with this arbitrary vector p naught p, and we're going to force it to be what?
0.
We're going to force it to be 0. Okay. So we're going to take -5, -2, and -1, and we're going to dot it with, what do we use as p, I guess, here I said p naught, but really I should be using what in this case? It was our common what?
P1.
Our common tail, right? That common point that we used? Does that make sense, folks? P1 is our common point, so I shouldn't put P naught, I should put P1. Okay. So then this would be, what's this vector? It would be x minus x naught, or P1, y minus 1, z minus 1, and we're going to set that to be 0. Okay. Take a moment here, folks. I need everyone to be on board with this. Okay. I know some of you are feeling good. I need everyone to be on board with this before we move on. Yeah.
Where'd you get the x minus 1, y minus 1?
Yeah, so here's the vector. So remember that P is some arbitrary point, right? So P is some arbitrary point x, y, z, right? It's my variable. That can be anything. As long as when I take and construct that vector and I dot it with n, I get 0, it's a point on my plane.
Cool.
Okay? And where did I get this expression from, folks? I did my arbitrary x, y, z minus the vector p1, which was the vector, in this case, 1, 1, 1. Okay? If you had done everything with, this is why it was important to do this, though, folks, because if you'd lined everything up with vector p2, then that's what you would use as your common tail at this point right here. Okay. How are we doing, folks? Okay, so to Bridger's point, you could have started building the equation ABCD with x, y, z in there, and then plug in a point and then solve for D. But notice that this is actually done. We're done. This is the equation of the plane. And you'll actually see a lot of times in my notes, I'll stop writing it there, because what have I given you? An equation of a plane. As long as x, y, and z satisfy this equation, then our point is on the plane. Okay? But to make it look like the algebraic form, what could you do?
Expand it out.
Expand it out. What do you mean by expand it out? Well, actually compute the dot product, right? Actually compute the dot product, so you'd have -5 times x minus 1, minus 2 times y minus 1, minus 1 times z minus 1. And now that equals 0. And now this looks like what you expect the equation of a plane to look like. And you could continue simplifying it until you've identified what that d is.
That's what the MAT had us
Yep.
do.
Yep. Okay. How are we doing, folks? Yes, Elaine. Elaine?
Eliana,
Eliana, I'm so sorry.
on
Oh,
the
yeah.
exam, would the first form be okay to write that?
Correct. I would accept this form, I would accept this form, unless I say I need you to put in a particular form. If I say find an equation of a line, you've got to give me an equation of a line. Whether it's, there's lots of ways we could do that. Parametric, symmetric, vector. If I ask you for the equation of a plane, you've got to give me an equation to a plane. And so I would accept this or this. I kind of like leaving it here. This is nice and compact, and what? It reinforces the definition of a plane over and over again, which I think is really important to do. Okay, folks, I appreciate your patience. Let's go ahead and take a break here. Okay, so let's make some statements about planes. Two distinct parallel. Did we say the angle on this side? No, we haven't said it yet. That's okay. Two distinct parallel planes will never intersect. Okay? So if I have, here's a plane, and here's another plane. Those two distinct planes we would say they're parallel. Now, I actually haven't defined what I mean by parallel planes yet, or by an angle between two planes, right? What do we notice about these two planes?
Same normal vector.
They both have, well, not necessarily the same normal vector, exactly, but what?
The normal vectors would at least be parallel.
The normal vectors are parallel to one another, and so as long as the two planes, one contains a point that the other doesn't, then these are distinct planes that never intersect. Okay? So, in fact, we're going to start talking about the angles between planes, and the way we're going to do that is talk about the angles between the normal vectors. That's what we'll do down at the bottom of this. Okay? So, two distinct non-parallel planes will intersect along a what? So I want everyone to try this. Draw one plane. I want you to draw another. So remember, this plane extends forever. It's not a squared space. It's a plane. It extends forever. I want you to draw a second one, and it cannot be parallel to this one. So I can't draw it stacked like I did here. So what would this have to look like? We've got two non-parallel planes here. What do we notice about their intersection?
Has to be a line.
They intersect along a line. Okay? I want to point out that I'm exploring some facts about planes that you could go and discover any point in time you want to as well. You just play around with them, and you'll rediscover these facts. Okay? I'm discovering these facts by doing what though? Drawing quick little sketches to think about things. I'm not worried about drawing accurate sketches, but I am drawing some sketches to help me think about things. So two distinct non-parallel lines will intersect along a line. Okay? Two non-distinct planes share all points in common. There's nothing to say there. Two planes are orthogonal if what?
Their normal vectors are orthogonal.
Great. If they're orthogonal, or if their normal vectors are orthogonal, two planes are parallel, or excuse me, two planes are perpendicular if they're orthogonal, or if their normal vectors are orthogonal. So how could we check that? How can we check to see if their normal vectors are orthogonal?
If there's a normal vector on the like the surface defining the other plane?
Ooh, that would be true. That would be true. That'd be kind of hard to check. That would definitely be true, 100%. What's a quick way to see if two vectors are orthogonal? What do you say, Caesar?
Dot product?
If their dot product is 0. Is that what you're going to say, Alex? No. What were you going to say?
Yeah.
It is what you're going to say. Okay, yeah. So, i.e., two planes are orthogonal if when you take the dot product of their two normal vectors, you get 0. That means the two planes intersect one another at 90 degrees. Okay. Two planes are parallel if n1 is equal to a n2. What did I just say there? Two planes are parallel if what? So here I've got two vectors, and what am I saying about these two vectors? One is a scalar multiple of the other. What's that the definition of? The vectors being parallel. So two planes are parallel if their normal vectors are parallel, i.e. if one normal vector is just a scalar multiple of the other. All right, so folks, I don't have anything more to teach you in this section. Okay? Everything else is just putting together the topics that we've covered. There are lots of different problems that I can ask. There's kind of a whole array of them, right? It's almost infinitely many, not really. There's probably, I don't know, 100 different types of questions I could ask. We're not going to work all 100 different questions. You're not going to try to work all 100 questions. You are going to work all the questions I ask you to work, but you're not going to try to work every single possibility. Instead, you're going to try to take what you've learned about what do I need if I'm coming up with the equation of a line, what do I need if I'm coming up with the equation of a plane, and then try to tailor that to the situation I've given you. So for example here, folks, let's see how we would do this problem together. We'll set it up, and at a certain point, we'll leave it, because we'll stop the computation. Okay, but let's set it up. So I want you to find the equation of the line where these two planes intersect. Now, folks, here I drew a little sketch for you because I know that on the board I have a hard time. I don't think this is an accurate sketch. I don't believe it is. Okay? But I do know that these two planes aren't what? Let's mention that. They're not parallel. How come? How come? Because what's the normal vector of the first one? We can read it right off of the equation when it's in this algebraic form here. We can read the normal vector as 1, 3, -1, right? That's the normal vector. What's the normal vector of the second plane? Or I should say a normal vector. I'll be a little more careful. It's the vector 1, 1, 1. What do we notice about these two vectors? They are not parallel, because one is not a scalar multiple of the other, right? So I know these two planes aren't parallel, so they are going to intersect. What does the intersection of two planes look like? A line. Does it matter how carefully you draw those two planes? No. Their intersection is a line. So what am I asking? At the heart of this problem, I'm asking you to do what? Come up with the equation of a line. Yes, there's the specifics of this question here. Put that aside for a minute. If I'm asking you to come up with the equation of a line, what do you need to do? We need a direction vector and a point that we pass through. Okay? Let's go first find a point that we pass through. Okay? We need to find a point that's on both of these planes. And let's see here. What could we do? Let's start by adding these two equations together. I think we will eliminate one variable if we add these two equations together. Okay? So if I were to add x plus 3y minus z equals 1, if I were to add that equation to this equation here, that would give me the equation 2x plus 4y is equal to 1. Okay. So now I can just pick I can pick whatever x coordinate I want, right? So I just want to point out that there's a lot of x coordinates, like this line extends on forever, and for any x coordinate I pick, there's going to be some point that we can find a corresponding a point on this plane for. So let's pick I don't know, how about x equals,
0.
sure, let's see if we do 0, that'll work, just trying to avoid fractions here. I think I'd like to pick, well, I don't know if we're going to be able to avoid fractions because of the way I set this up. So let's just go ahead and pick x equals 0. Sure. Okay. So let's pick x equals 0. If I pick x equals 0, what would y have to be, folks? Y would have to be 1/4. Implies y is equal to 1/4. If I pick y is 1/4, now I know an x coordinate and a y coordinate. Just a second here, folks. 0. Zero 1/4. Yeah, okay, great. So that if we go ahead and plug this, these collection of points into either of these equations, we will then find a corresponding point that's on both of these planes. Okay? So let's see here, if we take and plug these into the first equation here, we would get 0 plus 3/4 minus z has to equal 1. And if we solve that for z, we would get that z is equal to negative 1/4. Notice that if I were to plug those points into the other equation, it again satisfies it. So what have we found? A point that's in both planes, right? So folks, sometimes people say, how did you do this? And I had to pause and think about it for just a second. I went ahead and solved these two. I went ahead and eliminated one variable here to get me down to a point where I just had an equation with two variables. Now I can pick one coordinate and then find out what the other coordinate would have to be. Now I've got two coordinates that have to be on both planes, and then we can find the corresponding z coordinate. Bridger.
Could you add 1 to each side of the equation for q, then set the left sides of both p and q equal to each other and solve for a similar equation to the two extremes?
That would work, yes, but you're still going to have the point where you're going to have an equation that has both, has all three variables in it, and eventually you want to try to find a common equation that has fewer variables, then pick one coordinate so the other one has to be fixed, and now you've got two fixed coordinates that are on both, that satisfy both sets of equations. Yeah. So one thing that I kind of was fumbling over, folks, and I was a little tired. If I add these two equations together, I get an equation that encodes both the information from both of these equations. And so finding a point that's on in this equation means that that point would be satisfied both of these equations as well, but there would be a common point. So. Okay, so we've got a point. That was kind of a mess, folks, but everyone see that? We've got a common point. The common point would be 0, 1/4, minus 1/4. That's a point that's on both planes. How are we doing? Right? Because what do we need if we're coming up with the equation of a line? We need a, what for equation of a line? A point and a direction vector. So next thing I need is a direction vector. And here's where I'll leave you to do the calculation. Okay? What are we going to do to find the direction vector? What do we notice? This requires, so this is where I've never taught you how to do this problem. I still expect you to be able to do this problem. Now, careful, you're going to get more practice, more intuition, but it's not that, oh, Charles showed me how to do this problem, so now I know how to do it. There's something that you need to observe in trying to find the direction vector for this line here. There's some fact that you have to observe somehow. You give everyone a second to look at it. I know some of you see it, but some of you are still looking. I want you to take a second to see what can you notice. So where's my direction vector? So you say this is the point that I just found. There's that point. Maybe there's my direction vector. What do I notice about that direction vector?
Orthogonal to the normal vector.
Which normal vector?
For
What's that? both of them, right? Right? Because this vector lies in, say, let's say this plane right here. If it lies in this plane right here, it must be orthogonal to this plane's normal vector, right? But it also lies in this plane right here. Let me color code them so I can talk about them. Okay. This red, let me make it. No, I want that to be. So for the red plane, we've got this normal vector. For the green plane, we've got this normal vector. And what do we notice about our direction vector v? So that's the observation that we need to make, right? Does everyone see that? Okay. So this is where I don't have to tell you how to do this problem, and I won't. In fact, my hope is that when you get to the test, you encounter one that you haven't seen. Okay? Now that sounds unfair, but it's not. It's just like any other, like when you were learning lines, remember that? And they said, we want you to come up with an equation of a line that's parallel to this line and passes through this point. There's all sorts of different questions I can ask you, but they all involve, could you build the equation of a line? Okay? So that's what we're doing here. Okay? So we found a point that we passed through, and then we needed a direction vector. Well, where's my direction vector? It's this black vector right here. But what do I notice about it? It's orthogonal to green's normal vector, and it's orthogonal to red's normal vector. So how could I find v? If it's got to be orthogonal to both these vectors. It's the cross product of what? The two normal vectors. It's the cross product of n1 cross n2. What if somebody else did the cross product of n2 and n1? Not a problem. They're just going to find a different direction vector. In fact, let's make sure I set this one up right. Index, so I've got it. Index for the first. Nope, I've got it going the wrong way. So technically I should draw my vector going this way if I want my picture to be accurate, which I've said we don't worry about, but if I want my picture to be accurate, v would be going this way. Yes?
If you wanted to, or if you didn't want to do like the normal vectors, could you also find your direction vector by, if you had 2 points? Like if you solve your system of equation, there's 2 points.
Yes, that's another way you could do it.
Okay.
Yep, so again, folks, there's no one way to do these problems, and that's where you're developing your intuition. And again, if I were to just say, this is how you have to do this problem, or if I say, let me show you how to do this problem, you'd never think of that way of doing it. There are lots of ways to do these problems, and that's where you're going to grow. What you need to understand is the big picture. How do we find the equation of a line? How do we find the equation of a line, folks? We need a point and a direction vector. Okay? We did algebra to find a point. We found a equivalent equation, found a point on it, and then back substituted to find v. Okay? Notice we didn't have to find one point. We could pick. There was a choice there. You could have picked any number you wanted for x or any number you wanted for y, and then everything else was determined after you did that. Okay? So then we've got a point and we've got a direction vector, and so our answer would just be r is equal to that point 0 1/4 minus 1/4 plus t times v. Where am I going to get v? So I'm just going to write v1, v2, v3. But how would I get v? By computing that cross product there. Yeah.
Doing it the way that he said, we would just pick a random point on that line.
So if you had picked some other point, here I picked x equals 0. If you picked x equals 1, you would have found another point that was on this line. Then you could find the vector that took you from one of those to the other, and that could be your direction vector. Okay? Yeah, there are many ways to do these problems. It's what makes grading this class really, really tough. But that's how it goes. How we doing? All right. Folks, what I did here is in anticipation of exactly what's happening. You have solutions to all these problems here. I want you to take a look at them and come by and see me with questions on these. Okay? Do I have anything else I want to say? I think I had the issue of the angle. Did I say that here? So here, folks, here's just this one last fact to just highlight. I don't have anything to say about it. But the angle between two planes is the smallest angle between their normal vectors. So this is the last statement, number 30. So if I have two planes here, if I want to find the angle between two planes, I'm just going to take, the first one will have a normal vector that points like this, and the second one will have a normal vector pointing like this, and I'm just going to compute the angle between their normal vectors. This theta right here, that's what we call the angle between two planes. Okay? How do you find the angle between two vectors? There's lots of ways, but what's one good way? The dot product, and because the geometric version of the dot product has a cosine of theta in it, and you can solve for theta. Great. Okay. You good? No, that's the 13.6. If you don't need one, please let me know. Maybe extra. Sorry about that. No, it's okay. It's just oh yes. Oops, sorry. Here's one for you.
Wow, I didn't charge that way. I thought it was representative. Did you see me looking for some? I brought pencils, right?
Do I have any spare copies floating around?
I forgot paper.
Oh, I gave her one. Okay, great. Everyone have a copy? So folks, we're just going to scratch the surface of this one. I want to point something out to you. The first thing I want you to learn how to do is how to name these quadric surfaces. Okay? And I actually give you, so this is my hint for how to name them. This is my hint for how to name them. Okay? For the surfaces we studied, I don't know if this is true beyond the surfaces we studied. This is just the pattern that I've observed in the ones we look at, so don't extend this. But for the surfaces we studied, if two or more orthogonal traces have the same conic section type, we affix the suffix oid to it, as in paraboloid, ellipsoid, hyperboloid. Okay? If two of the traces have the same type of conic section, let me just make sure. If two or more, because ellipsoid has all three traces are ellipses. If two or more of the traces are the same conic section, then we put the word oid at the end of that conic section. Okay? If only one trace of the three orthogonal traces is of a particular conic section, then we affix the word, or the phrase ick onto it. So this is just my observation, but I think it helps, like students have always struggled with naming these surfaces, and that's how this is how I remember them. Okay? So let's go ahead and click first that first link. So let's look at, for example, the ellipsoid. Okay? If you were to look at the trace, if you were to look at the trace of this in, let's do first the x. Oh, I can't draw on this. If I were to do this in the xy plane, the trace is an ellipse. Same with the yz plane and the xz plane. They're all three ellipses. So we would say that this is an ellipsoid, because two or more of the traces were of the same trace. Okay? If I were to look at this conic section here, we see that if I were to let z be some fixed constant, if it's 0, that's just the number 0, that's just that point down here. But if z were any other positive constant, like 1, then this would be an ellipse. But there's just one trace that looks like that. The other two traces look like this. When y is 0, or when y is a constant, that's a parabola. And when x is 0, or any other constant, that's a parabola. So there's two parabolas, right? So the word is going to have, the name for this is going to have paraboloid in it, right? But it also had an ellipse as one trace, so I'm going to call it an elliptic paraboloid. Okay? Folks, I usually will not nitpick if this is a circular paraboloid, or because if these two values are the same, then it would be a circular paraboloid. Okay? I won't nitpick about that. If it is a circular paraboloid, I'll call it that, or I'll call it an elliptic paraboloid. Okay? Let's do one more to make sure that's making sense. Okay? So here, if I were to look at the traces, if you were to look at the trace in the let's see. That's true with the I guess with the hyperboloids. We're not going to call it an elliptic hyperboloid, although I think you could. That if you were to look at the trace in this direction, it's an ellipse, and then these two are hyperbolas. Usually we just drop off the elliptic part and we just call it a hyperboloid. But you'd be more precise if you called this an elliptic hyperboloid. Meaning in the YZ plane, the trace is an ellipse. In the other two traces, it's an hyperbola. Are we seeing that, folks? Okay. Folks, you know, the reason why we do the pre-work is because there's just, I don't know if you're noticing it, there's just not enough time, right, to get through all the content. You can look how I mapped up the sections we're supposed to cover. There's no wiggle room in there. And so please, please do go back and rewatch those pre-works if you're having trouble with this. But I'm assuming you've got that idea of traces already down. If you don't, that's okay. Please, when I say I'm assuming it, it doesn't mean like if you don't know it, you're out of luck and I won't help you. It just means I don't have time to go through it in class, but I always have time in office hours to go through it with you. So we'll do a couple more of these. Let's see here. Here, let's do this one here. So if we were to look at the trace, still can't draw on this. If we were to look at this trace right here, that trace is a paraboloid, or excuse me, a parabola in the XZ plane. Everyone see that parabola? And if we were to look at the trace in the YZ plane, it's another parabola. So I got two parabolas, right? But if I were to look at the trace in the XY plane, if I were to look at the trace in the XY plane, it's hyperbola. So I have one trace is hyperbola, and two are paraboloids. Excuse me, two are parabolas. So what's the name of this? Hyperbolic paraboloid. Okay. Giving the right name to these is not the most important thing we do, but it helps you to start organizing these. Okay. I've built for you, and I strongly recommend, folks, that you practice this. This will be very beneficial to you. We're going to learn how to sketch these. We'll get better at sketching these as we go along. And you're learning how to do that in the MyLab Math. But this is the sort of level of understanding that I'm looking for right now. It's being able to assign the names and being able to identify various pieces. So this is hyperlinked into the electronic version of this. I built this question. It runs through all possibilities. It's a My Open Math question. You try it 3 times. You hit submit. Okay. You try a similar question, and it's a brand new question. It will just it's like your version of flashcards that you get to just try over and over again until you learn the names and can identify these various quadric surfaces. So the most important thing to take from this lesson 13.6 is being able to do this problem right here. This will show up in some of your My Open Math quizzes. Okay? But here's an opportunity. It's just a hyperlink straight to it. There's no logging in, nothing. You just click on this and you get to practice this over and over again until you've got these names down. Okay? So let's for example, let's see here. So let's, for example, look at this one here. If we were to let x be 0, what is this the equation of? We learned this in our review of the conic sections. What's that equation of? So I'm covering up the x.
And then
Not an ellipse, no. It would, because if I subtracted that over, it'd be a minus sign, right? Oh, I'm trying not to touch that. What would that be, folks? That would be a hyperbola, right? Good golly. And if I were to cover up the y right there, what would that be a conic section of? That's a hyperbola, right? So what have I got? Two hyperbolas, so the name's going to have hyperboloid in it. Okay? Why is it considered of two sheets? Okay, so that's something that you saw in your pre-work. Why is that one of two sheets like this? See, does this picture have two sheets? Yeah, this one has two sheets. Why is it of two sheets? Okay? The way I quickly identify that it's of two sheets is that when I let z be 0, there's no solution to that. Do you see that? So there are going to be some points on this. So for certain z values, there will be no corresponding points on the graph. That's how I quickly see that it's of two sheets. Okay? And that matches this description of it, but I'm not asking you to just memorize these. Instead, you want to think about it in terms of, are there solutions to the equations and what do they look like? So if there are, in this case, z coordinates where there are no corresponding points on the graph, there's going to be a break in the graph. But if I were to, instead of letting z be 0, I were to let z be something like 5, then there would be a solution to this. And it would be, if you do 5 minus 1, that'd be 4, and that would be an ellipse. So for certain z values, I get ellipses. For certain z values, I get nothing, which is why this is a hyperboloid of two sheets. Okay? This is going to take some practice. Okay? That's okay. You've got some time to learn these. The ones that you have to know right now are the hyperbolic paraboloid and the paraboloid. And I guess I should also add the ellipsoid. Those are the three that you have to know. Okay? The ellipsoid, the paraboloid, and the hyperbolic paraboloid. The hyperbolic paraboloid is the one that gives us that saddle point, remember, that you learned about in one of the pre-work videos? Okay. All right. So I think we're going to stop there for today, and I'm still failing in my goal to get caught up. That's okay. Folks, give me a couple minutes to do some announcements.